Hey everybody, this is Waehner from Confluent. Today I want to talk about end-to-end integration from Internet of Things and the Edge to Confluent Cloud and event streaming with Apache Kafka. In this session I will start with an overview about some different use cases, and then I talk about event streaming with Kafka and how that can help with IoT projects. I will cover a few different IoT architectures from hybrid to cloud. And then I will give 2 examples for connected car infrastructures, where you can see how this looks in the real world. Let's begin with the use cases. And here I have 2 exciting examples. So first of all, this is an example of Lyft, one of the ride-sharing applications in the US, similar to Uber. Both Uber and Lyft use Apache Kafka and event streaming heavily because the huge requirements are that you need to connect to millions of devices, in the end the drivers and the consumers, the customers, and need to correlate that data in real time. So you need to calculate in the backend things like the estimated time of arrival of the driver, the estimated time until you come to your final destination, and the estimated price. And of course there's many other correlations required, as you can imagine, like payment and fraud and so on. And as this has to happen for millions of users 24/7, and as it has to happen in real time, this is really challenging and critical infrastructure. So this also has very high workload. This is typically a deployment in Confluent Cloud with gigabytes of throughput per second. And so this is a great example for IoT, where you have devices and smartphones at the edge and connect all of that and correlate this data in real time at the backend services in the cloud. Another example is a connected car infrastructure at Audi, which they have built with Confluent several years ago to connect the information from all the cars on the streets and send it in real time to the cloud to correlate the data for different use cases like after sales, so more the customer related use cases, but also then for internal use cases like predictive maintenance. Here it's about all the sensors in the cars, and you ingest them into the cloud, do a lot of pre-processing and correlation, and connect it to other backend systems, which can be a data warehouse or data lake for analytics, but also real-time streaming applications where you want to act in real time on the data which happens at the edge. Like the Lyft use case, this one is also the same. It's connecting to millions of devices. It's real time, it's mission critical 24/7, and it needs large scale. So I think these are 2 very nice use cases to start this conversation about. And so I said already the term event streaming and with Apache Kafka. So how is that related and what does it mean here? With event streaming, I mean that you continuously process data. This means you really analyze the data in flight. So you don't store everything first in a data store at rest, like a data lake or database, and then analyze it in batch mode. For many use cases, this takes too long. You typically need to act in real time on information to make the most business value out of it, which can be increased revenue, customer experience, or reduced risk. And that's really the big point about event streaming. And this is not just one stream, but a correlation of different data events. Not just data from real-time events, but also, for example, a combination of real-time events which you correlate with data from a database, from a table. So a traditional database is where the data is stored at rest, right, in a DB table. And this is the passive data. And then you do an active query on that with HTTP and a web service, or with some other kind of request-response paradigm like SQL. So this is always in some kind of a too-late architecture, where the data is already stored at rest, and then at some point later you request it, which might be good for a report, but might not be good for continuously acting on data. And that's exactly what event streaming is, where the event stream is the active data, so you continuously process it, like in the 2 examples from Lyft and Audi. But then, of course, you can also do passive queries on top of that data to build stateful applications and to do analytics. So that's still required, and that's still possible. But this is in addition to the continuous processing of the data. This is the huge paradigm change between a traditional data store and event stream processing. And therefore, today we have streams which change data in real time. So in this case, it's a payment where each user does a specific transaction. This is each one single event in real time, And it's a stateless information which doesn't change after it happened. And then you also have tables like in a relational database or in a data lake, where you keep state and update things. Like after every payment, you also update this credit score with a business rule or with an algorithm or a machine learning model. And you keep that stream live, but you update it in a stateful way. So event streaming does not mean just stateless information, but you really keep the information of streams also in tables to have stateful business applications. Both is possible with event streaming. That's also very important to understand. So what I just explained is the left side. You push data, you continuously stream it. And on the other side, you still want to do analytics and you also want to query data, for example, from a mobile app. When you use your bank account and you want to know your own balance, for example. Or from a company perspective, you want to get the credit score from a customer before you give him a credit or loan. This is where you pull the queries from the streaming data. That's also possible with event streaming. And so event streaming, obviously, the de facto standard for that is Apache Kafka. So Apache Kafka was built over 10 years ago to do exactly what I described for these use cases. It's very important to understand that Kafka is not just a messaging system. That's just one core part of it. But actually it's a combination of messaging and storage and integration and processing. And all of that in real time at scale for huge volumes of data if you need that. And this makes Kafka so powerful and different from other traditional systems for implementing this, where you have to combine, for example, a messaging system like RabbitMQ or IBM MQ with another integration framework and a stream processing engine like Flink or Spark Streaming. With Kafka, you can combine all of that into one single mission-critical infrastructure. And that's the huge added value of that. So this is how it looks like. This is an event streaming platform using Kafka. The middle thing is the central nervous system where you have all these different events. The producers and consumers can communicate end-to-end in real time in milliseconds. So that's part of that. But you also store the data in Kafka in the middle to decouple everything. If one producer produces more data than the consumer can consume, then it falls behind. And that's okay because Kafka handles the back pressure. Or if one consumer isn't actually trying to process it in real time, but it's a batch system like a data warehouse, then you only ingest the data in near real time or in batch anyway. And that's totally fine because everything is decoupled with Kafka. That's also one reason why people use Kafka so much for microservice architectures, no matter if it's big data or small data. Kafka was built for scale from the beginning at the tech companies. So here's just a few examples. You can Google for any tech company in Silicon Valley and you can learn how they use Kafka under the hood for many mission-critical workloads. And Kafka is not just used for big data, that's also really important to understand. It's used for mission-critical deployments, including use cases like instant payment platforms and fraud detection use cases. This is often not trillions of messages, this is maybe a few thousands per second. But with the decoupling and the high availability of Kafka, that's the huge advantage of why people use it. And obviously, it's not just used by tech companies today. Every bigger company has several different Kafka projects for good reasons. The first use case often was data ingestion into Hadoop, but this is really more a small fraction of the use cases we see today, where we see so many use cases around Kafka. Let's take a look at a few of the IoT architectures for edge, hybrid, and global deployments with Kafka. You can run Kafka at the edge, and the edge can mean different things. This can be something like a retail store, this can be something like a data center, or this can be something really small, where you, for example, deploy Kafka in a train. We see all of these use cases in the real world. And therefore, it can be a single broker, or of course, if you need high availability, it's typically a distributed system of at least 3 brokers. But for example, when you deploy it in a factory for manufacturing to monitor and process the data on your assembly lines, then you deploy a cluster of 3 brokers in your factory to do edge processing with low latency and without having all these cost issues about implementing the replication of all the data to the cloud, which is very expensive for all the machines in the factory. So you want to do that at the edge and directly connect to different technologies. Like in a factory, it could be MQTT or OPC-UA, or even proprietary standards like Siemens S7 PLCs. And then you build your digital services and Kafka applications around that. And in addition to that, while you do all of that on-premise for low latency, for mission criticality, for data privacy, for reduced cost, you can also replicate some of the data to a central cluster, somewhere in another data center or cloud, so that you can aggregate the data from different systems. So it's typically a hybrid approach where you do some processing at the edge, like in a factory or in a retail store, or in a local region if you have a global deployment. But then you also replicate some of the data to the cloud or another data center where you can do aggregations, for example. So you could build one digital service. This can be something like an ERP system which you build in the cloud. And many of the customers or third-party vendors of this kind of software do this today. They build the most features in the cloud, but of course have some of the deployment at the edge for the reasons I mentioned already. And it's also not that Kafka is everywhere at the edge. It depends on your current situation. So in a new factory, for example, you might start with Kafka from scratch because it's open and standard-based and you can integrate with all your machines and PLCs. However, in some other factories, you might already have something running like Siemens MindSphere or Cisco Kinetic. And that's also totally fine. They all have Kafka connectors. So this is very, very flexible. And then you can use, for example, Confluent Cloud as a fully managed service of Kafka in its ecosystem, where you aggregate the data from all these different factories with different technologies and build your services on top of that in the cloud. And there's many different deployment options. I cannot cover this in detail here, but with Confluent Platform, you can even deploy multi-region clusters, which means you stretch one cluster over different regions. And they don't have to be close here. So we battle tested this with US East, Central, and West. So this means really it's one single Kafka cluster, but stretched about all over the US over many different kilometers or miles. And this provides automated disaster recovery, even if a complete data center or cloud region is down, without downtime and without data loss, and even including automated client failover without custom coding. And this is really huge for your mission critical use cases because this is really hard to implement and test by yourself. And then in the end, what we often see in IoT, and it's the same like for the Audi and Lyft use cases, we see global deployments with different architectures. We see data replicated between continents, and we see more local deployments for aggregation scenarios or for other use cases. You're really very flexible here, and this can be edge and hybrid deployments or multi-cloud. Here's an example about that. I want to show you how to build an IoT infrastructure for 100,000 connected cars. This is more or less also like the Audi example or like the Lyft example, so that you see how that looks like in the real world. So on the left side, you see all the car sensors. They are sending data to the Kafka cluster. In this case, we use an MQTT proxy to connect to the millions of devices and stream the data in real time. And then on the top left, we do some data processing and data correlation. For an example, also connecting to other systems like an Oracle database and correlating information from the stream with the more historical data from a table or from a CRM system, for example. And that's all happens still at scale and in real time, right? So that's the advantage here. And then we have different other applications which consume the data. In this example, on the right side, we use Kafka Connect to ingest everything into a database like MongoDB for building a digital twin, for example. But in Kafka, the strength is that different consumers are completely decoupled to consume the data. So in this case, at the top, we also use a Python environment where we consume all the data from the Kafka cluster to train an analytic model with TensorFlow. In this case, we have built an example for predictive maintenance with an autoencoder, where we do anomaly detection on all the engine information from the cars, like the vibration and the sensor spikes. And based on that training, which we do, by the way, here without a data lake like Hadoop or Spark, directly by consuming from Kafka. We then, after training the model, which is still a batch process and takes some hours, we deploy this model into a Kafka native real-time application for deploying the model to do detecting the anomalies from the real-time stream. So here the great thing about this architecture, it's very simplified because you have one pipeline for batch analytics like model training, for near real-time ingestion into a digital twin like Mongo, and for real-time predictions of all the data of each car. And this is one of the big advantages of using Kafka and its Kafka native technologies. But also third-party services, as you see here with MongoDB. And so this is a really great, exciting use case, and you can map this to many other use cases in the IoT environment. Here's how that looks like. I have also built a demo of that with our GitHub project. You can check it out on YouTube or on my blog. In this case, we use the architecture around Kubernetes so that we have built a template infrastructure which we can roll out on different clouds. So this is more or less like Audi did it. They started on AWS, but they knew from the beginning they will also have to go to China. And in China, there is only Alibaba Cloud. So they built one infrastructure to roll it out on different cloud infrastructures. But I also have a nice other example. This is a fleet simulation where we really run it natively on Confluent Cloud. This has the huge advantage that you have a fully managed environment. It's a serverless offering with consumption-based pricing. You only pay for what you use. And in this case, we're using WaterStream, which is a native Kafka Streams application implementing the MQTT broker. And it's fully compliant. This means you really have MQTT natively on top of Kafka. So just one ecosystem to monitor and no external MQTT broker like we had in the example before, where we use HiveMQ. So both approaches have their trade-offs and pros and cons. In this example, we use WaterStream and KSQLDB to continuously process the data from a fleet simulation for 15,000 trucks. Again, it's real-time, it's 24/7, it's processing at scale. And so with these two use cases, I hope you understand how you can do end-to-end integration from the edge to the cloud with event streaming and Confluent. So therefore, why do people use Confluent? I mean, for exactly what I talked about. We are focusing on Kafka and just on Kafka. This is where we have our expertise and our focus. We don't do anything else. And therefore, we have over 300 full-time engineers just working on Kafka and its ecosystem. And this is just the engineers, right? Confluent is much bigger today. And then we have a self-managed product, which you can run Kafka on-premise, like I discussed, at the edge, or in a data center, or in the cloud. And also we provide our fully managed cloud platform, which is a serverless platform, not just for Kafka, but also providing connectors, schema registry, KSQL, and other components in a fully managed way. Yeah, and typically this is a journey. So it's an event streaming maturity model where you start small, build your own pipeline, first use case, maybe even by yourself with open source, but then you want to roll it out over hybrid deployments, use fully managed services, and stretch it all over the regions or maybe even globally. So we recommend that you engage early with us because even in the initial setup, you can do many things wrong depending on your SLAs and your high availability requirements and throughput and latency and so on. Just let us know if you have any interesting use cases. And also, please let me know what you thought about this talk and connect to me on LinkedIn or Twitter. I'm glad to get any feedback from you. Thanks for watching.